Okay, so now let's look at some more examples finding limits. So as always, the first thing we want to do is try to direct substitute into the limit. So if I'm trying to find the limit as x is approaching 4 of x squared minus 3x minus 4 over x minus 4, the first thing I want to do is I want to direct substitute. So if I'm direct substituting 4 in, that gives me 4 squared minus 3 times 4 minus 4 all over 4 minus 4. So that gives me 4 squared 16, 16 minus 12 minus 4, all over 4 minus 4. And so that gives me 0 over 0. That indeterminate form 0 over 0 should jump out at you and scream to you because we can't divide by 0. So we know 0 divided by 0 does not exist. So that means direct substitution fails. So if you see 0 over 0 by direct sub, now you want to go through, and that should be a clue to you, okay, this limit probably exists. I'm not going to say always because there are cases, very rare cases, where the limit won't exist if it's 0 over 0. But it should stick out to you and scream at you saying, okay, I got to do some algebra or use some trig now to figure it out. So in this case, algebra. So if we think about it, we've got an x minus 4 in the denominator that's sticking out at us. So because direct sub doesn't work, now we've got to figure out a way to rewrite this limit so that we can find an equivalent function that agrees everywhere but one point. So to do that, so let's think about what we can do. So if we do the limit as x is approaching 4 of our original function, and you always want to start out writing your original function because that's the limit you're trying to find. Well, now we need a way to rewrite it. So if we think about it, okay, maybe we can factor. So this is still the limit. So notice I'm not saying these functions are equal. So limit as x is approaching 4 of x minus 4 times x plus 1 all over x minus 4. And now, okay, I have a common factor of x minus 4 in the numerator and denominator I can cancel out. But it's important to remember, we're not setting the functions equal to each other, just the limits. Because remember, when I cancel this x minus 4 out, I've changed that function, right? And so we're finding a function that agrees everywhere except for at x equaling 4. So we're not saying that the functions are equal, just that their limits are equal. So we're using that rule, that theorem about functions that agree at all but one point. So if they agree everywhere except 4 at our x equaling 4 in this case, then we know those limits are equal. The functions themselves are not equal. So if you don't have the limit notation here, and you write that x squared minus 3x minus 4 over x minus 4 equals x plus 1, then you will lose points because the functions themselves are not equal. Only their limits are equal. So make sure you're carrying that limit notation through everywhere. You've got to carry that limit notation until you direct substitute. So at this point, now I should be able to direct substitute 4 in and get a value out. And so that's exactly what we're going to do. Now 4 plus 1, I've direct substituted. So because I've substituted, I've found that limit at this point. I don't have to carry that limit notation anymore. So now I can drop that limit notation. I could not drop it before this point because we had not found that limit yet. But now that we have, we know that limit is 5. So a similar one, limit as x is approaching negative 2 of x squared minus 4 over x squared plus x minus 2. Again, the first thing you've got to do, direct substitute. So when we direct substitute, this gives us, since we are substituting in, no limit notation, and so we end up with negative 2 squared minus 4 over negative 2 squared plus negative 2 minus 2. So negative 2 quantity squared is 4. 4 minus 4 over 4 minus 2, or plus a negative 2. So 4 minus 2 minus another 2. So 4 minus 4 is 0. 4 minus 2 is 0. So again, 0 over 0. Oh no, what do? We got to do some algebra. So finding a way to rewrite it, again, let's try factoring first since we've got a rational function. So usually if you have a rational function, first thing that looks like a polynomial over a polynomial, first thing you want to try is factoring. if you can factor, factor, because chances are you're going to have a common factor that'll cancel. So this becomes limit as x is approaching negative 2 of our original function, x squared minus 4 over x squared plus x minus 2. Now I'm factoring this, so x is approaching negative 2, but then x squared minus 4, so remember, how does that factor? Well, that's our difference of squares, so x plus 2, x minus 2. Again, make sure you're including your parentheses around your factors. All over, so x squared plus x minus 2, that's going to factor as x minus 2 times x plus 1. Now we have a common factor of x minus 2 in our numerator and denominator that are going to cancel. So it's this limit. The limit is x is approaching negative 2 of x plus 2 times x minus 2 over x minus 2, x plus 1, which was our original limit. Now we can say that's equal to the limit of just x plus 2 over x plus 1 because those two functions agree at all but one point. So again, we're using that theorem. And at this point, well, what was causing our issue in the beginning? It was dividing by 0. So because we would have been dividing by 0, now looking at this, there is no more 0 in our denominator. If we think about what would happen if we were to substitute in, negative 2 plus 1 would not be 0. So now we can direct substitute. So this becomes negative 2 plus 2 over negative 2 plus 1. Negative 2 plus 2 is 0 over negative 2 plus 1 is negative 1. 0 divided by negative 1 we can do because negative 1 is not 0. And that is 0. So that limit in this case is 0. Alright, the next one looks a little bit more challenging, but it's really not. So the limit is x is approaching 0, 1 over x plus 4 minus 1/4 all over x. The secret to this is figure out what the common denominator of your numerator is. Wherever the complex fraction is, so wherever your fraction is inside the fraction, overall, that's what you want to find the common denominator of, and just multiply the numerator and denominator of the overarching big fraction by it, and that's going to clear your fraction, the complex fraction, out. So in this case, we still want to direct substitute first though. So if I direct substitute first, this becomes 1 over 0 plus 4 minus 1/4 all over 0. And so that's 1/4 minus 1/4, so that's 0 over 0. Again, oh no, right? So let's try rewriting it. Limit is x is approaching 0. 1 over x plus 4 minus 1/4 all over x. Well, now we want to use that trick that I just told you. So this becomes limit as x is approaching 0. We still got all this here that we got to do some work with. But we're going to multiply this entire numerator and denominator. We're not changing it because we're multiplying by the same thing, by whatever the common denominator of 4 and x plus 4 are. So let's just say it's 4 times x plus 4. And multiply the numerator and denominator by that. So we do that. And so, okay, so 4 times x plus 4 times 1 over x plus 4. The x plus 4s are going to cancel out. We're going to be left with 4. So this becomes the limit as x is approaching 0 of 4 minus, now 1/4 times 4x plus 4. So the 4's cancel, so I'm left with just x plus 4. So 4 minus the quantity x plus 4. Again, make sure you have your parentheses there because otherwise that negative's not going to carry through to both pieces. All over 4x times x plus 4. Now, I'm not going to multiply this through right now, and you'll see why in a second. But what's going to happen is something's going to cancel. So if I clean this, just keep cleaning this up. So this becomes still limit as x is approaching 0. We're still carrying that limit notation with us because we haven't found the limit yet. So 4 minus x minus 4 just becomes negative x. So this is negative x over our denominator of 4x times x plus 4. And now I can cancel that x out. So this becomes the limit as x is approaching 0, negative 1 over 4 times x plus 4. And now we've taken care of dividing by 0, so we can directly substitute. So this just becomes negative 1 over 4 times 0 plus 4, which then becomes negative 1/16. All right, D looks a little bit similar, so we've still got stuff going on, so it's not a pure rational function because it's not a polynomial just divided by another polynomial. Now we've got a radical in our numerator, so the limit as x is approaching 3, square root of x plus 1 minus 2, all over x minus 3. So first thing we want to try, of course, what is it? That's right, it's direct substitution. So we try direct sub. So limit as x is approaching 3. We're substituting now, so there is no limit notation anymore. So that gives us the square root of 3 plus 1 minus 2 over 3 minus 3. So square root of 3 plus 1 is 4. Square root of 4 minus 2 over 3 minus 3. Well, square root of 4 is 2, so 2 minus 2 over 3 minus 3. And that gives us 0 over 0 again. Oh no, what do we do? So if you have a radical expression in your function that you're trying to fix a 0 over 0, or some other way that doesn't work, well, you want to think, okay, how can I rationalize either my numerator or my denominator? In this case, wherever the radical is, that's where you want to rationalize. So in this one, I want to rationalize the numerator. So I know that's contrary to everything we told you in Math 171, that you don't want to end up with a radical in the denominator. It's okay. For something like this, it's okay to have a radical in the denominator. So we're going to put that radical back in the denominator now. So limit as x is approaching 3, square root of x plus 1 minus 2 over x minus 3. And so to rationalize this numerator, it's the exact same process as rationalizing the denominator. You want to multiply by the conjugate of your radical expression. So in this case, my radical expression is the square root of x plus 1 minus 2. So if I want to get rid of this and move it down to the denominator, my conjugate is going to be the square root of x plus 1 plus 2. So remember, to find the conjugate, you just change the sign in between the pair of terms. Just swap the sign. So if it's subtraction, change it to addition. If it's addition, change it to subtraction. And make sure, it's extremely important that you're putting parentheses around all of these factors, because otherwise you're going to be losing stuff and making the multiplication not be right. You're going to be writing out mathematical lies, and you don't want to do that, right? Plus you'll lose points. So make sure you're putting your parentheses around everything, keeping everything that's supposed to be together, and not making things that don't go together. Alright, so now let's multiply this out. So square root of x plus 1 times square root of x plus 1. So still inside our limit notation, this gives us just x plus 1, because remember, it's square root of x plus 1 quantity squared. Minus 2 square roots of x plus 1 plus 2 square roots of x plus 1, and then minus 4. So remember, you're just falling here. My denominator, just like the last one, I'm not going to multiply this back out right now, because hopefully something's going to cancel. So I'm just going to leave it as it is for now. I know it's an ugly denominator. That's okay. It's okay for it to be ugly at this point. So this becomes the limit as x is approaching 3, x minus 3, all over this ugly thing of x minus 3 times the square root of x plus 1 minus 2. Notice now my x minus 3's will cancel. I'm getting rid of that division by 0. So this is going to become the limit as x is approaching 3 of 1 over that ugly radical plus 2. So square root of x plus 1 plus 2. And so then that gives you 1 over, at this point, now we're direct substituting because we've taken care of dividing by 0. So square root of 3 plus 1 plus 2. So 1 over square root of 4 plus 2, 1 over 4. Alright, now let's look at the limit as x is approaching 0, tan x over x. So again, first step, direct substitute. So if we direct sub in now, this becomes the limit, or no longer a limit because we're substituting in. So tan of 0 over 0. And without a calculator, hopefully you know that tangent of 0 is 0. So this gives us 0 over 0. Again, big issue, right? So that should be a clue. It exists. So let's try rewriting it. Well, we can't do algebra here, but instead let's think trigonometrically. How can we rewrite this? So the only thing we could do, well, we know tangent is what? That's right, tangent is sine over cosine. Sine x over cosine x. So sine x over cosine x all over x, still inside the limit as x is approaching 0. Now, cleaning this up, this just becomes limit as x is approaching 0 of sine x over x cosine x. Well, we still got that 0 over 0, right? Because sine of 0 is 0. And we still got the 0 in the denominator for x. So what can we do? Well, you should hopefully recognize at this point that you have limit as x is approaching 0 sine x over x here, right? One of those special trig functions I told you to memorize. So we can rewrite this now as a product. So this becomes the limit as x is approaching 0 sine x over x. That special trig function that you should have read the proof of in your book, proved by the squeeze theorem, times now what's left over. So limit as x is approaching 0, 1 over cosine x. Or if you want to rewrite this as secant x, that's fine. And so then now, limit as x is approaching 0, sine x over x is 1. So this just becomes 1 times and 1 over cosine 0. At this point, we can substitute because cosine of 0 is not 0, right? So that means this is 1 times 1 over 1, or 1 times 1, which is 1. And we're done. Now let's look at part F. So the limit as x is approaching 0, sine of 4x over x. Again, direct sub, this becomes then sine of 4 times 0, or sine of 0 over 0. And that gives us, alright, so sine 0 over 0. Well, we know sine of 0 is 0, so this is still 0 over 0. So, again, that should be a clue that the limit exists, right? So if we think, okay, well, maybe we can use our special trig form. So if we look at this, limit as x is approaching 0, sine of 4x over x. Well, to use that special trig function, it has to be sine of the same thing over that same thing. So sine of blah over blah, where blah is the same in both the numerator and denominator. Well, in this case, we have 4x here inside our sine function, but we only have 1x in the denominator. So how can we fix that? Well, we can multiply and divide by the same number, right? That's not going to change anything. So if we do that, limit as x is approaching 0, of sine of 4x over x, right? Well, if we need we've got to have the same thing. So if I need a 4 in the denominator, so I can divide by 4. But if I multiply by it in my denominator, I've got to multiply by it in my numerator as well, or I've changed the function, right? So now at this point, okay, I can pull this 4 as a constant out of the limit. I want to leave the 1 in the denominator there, so it's the sign of blah over the same blah, right? But then if I rewrite this, now this is 4 times the limit as x is approaching 0, sine of blah over that same blah, where blah in this case is 4x. Now I can use that special trig rule because it's the same in the numerator, or inside the sign in the denominator. So then it just becomes 4, limit as x is approaching 0, sine 4x over 4x, we know is 1 by our special trig function. So this is just 4 times 1, which then becomes 4. Alright, g is very similar, so limit as x is approaching 0, sine x over 7x. Now our issue is they still don't match inside sine in the denominator, but now we've got this extra 7 here, right? But remember, what is 7? It's a constant. So, and I can go ahead and tell you, if you direct sub into this, you're going to get sine of 0 over 7 times 0, which is still going to be 0 over 0. You still got to show me that. But now, think about 7 is a constant, so if I want to rewrite limit as x is approaching 0, sine x over 7x, right? Well, remember, I can factor constants out of limits, right? That was one of our limit rules. So then this becomes 1/7. Keep in mind, because the 7's in the denominator, you got to factor the numerator out also, so factor the 1 out to keep it as a fraction. So 1/7 times the limit as x is approaching 0, sine x over x. Now there's our special trig limit, right? And so then we know this is 1/7 times 1, or just 1/7. And we're done. Last one. So limit as h is approaching 0, 1 minus cosine h quantity squared over h. So again, looks similar to one of those special trig functions, but first thing we want to try is direct substitution, right? And so what do we know? So we know this is going to be, by direct substitution, 1 minus cosine of 0, quantity squared over 0. Well, 1 minus cosine 0, what's cosine 0? That's right, it's 1. 1 minus 1 over 0. 0 over 0, oh no, right? Do something. So, limit h is approaching 0. Well, what can we do? It looks similar to our special trig limit, but our special trig limit is only 1 minus cosine x over x, or 1 minus cosine h over h, right? It doesn't matter what we call a variable. But in this case, it's squared. Well, what's that mean? If we square something, what are we doing? We're multiplying it by itself, right? So this is going to become the limit as h is approaching 0. Rewrite our original one first, 1 minus cosine h quantity squared over h. And then this becomes, so if we think about that, right, this is limit as h is approaching 0, 1 minus cosine h times 1 minus cosine h, all over h, right? Well, now, okay, here's my special trig limit, right? So I can rewrite this. This is the special trig limit times 1 minus cosine h. So then this becomes limit as h is approaching 0, 1 minus cosine h over h. There's our special trig limit. Times limit of the product is the product of the limit. So times limit as h is approaching 0 of our other 1 minus cosine h. Well, now we know 1 minus cosine h over h. That is our special trig limit. And so we know that's 0. And then we can direct substitute into 0 in for 1 minus cosine h, right? So this just becomes 0 times 1 minus cosine of 0. Cosine of 0 is 1. So this becomes 0 times 1 minus 1. Or 0 times 0, which is 0. So our limit as h is approaching 0 of 1 minus cosine h quantity squared over h is 0.